Below you is a new 150,000 pound 1500 psi fluid bed combustor as manufactured by ASEA Stahl. Run-of-mine Wyoming subbituminous coal is received at the job site by railroad hopper cars and dumped through this 6-inch by 9-inch grizzly into the collecting hopper below. It is then elevated by this 18-inch drag conveyor and bucket elevator to the top of this 30-foot diameter, 96-foot tall, 220-ton storage bin. The coal containing up to 27% free moisture is recovered from the bottom of this silo by this live bottom bin and weigh belt feeder at a rate as called for by the fluid bed combustor. It then drops down into a Williams number 15 by 20 single roll crusher, producing a 2 by 0 inch product. The 2 by 0 coal is then elevated by a 12-inch drag conveyor to the top of the Williams number 43 DF roller mill located on the outside. When preparing fuels for circulating fluidized bed combustors or fluidized bubbling bed boilers, the Williams DFM mill has certain advantages. Number 1, surface moisture for coal of up to 27% can be handled without derating. Number 2, fines are pre-stripped from the feedstock by hot air, thus reducing over-grinding and subsequent carbon loss from the combustor. Hot gases entering at the wind box surrounding the mill cause a partial fluid bed inside the pulverizer. The computer operating the DFM mill controls the speed of the mill so as to grind at a rate matching that of the feed system. Slow speed grinding does not generate excess fines. The main vertical shaft is driven by a remote right-angle Falk gearbox coupled to a standard 50 horsepower motor. The motor in turn is connected to a variable speed drive, resulting in a grinding system with infinite turndown. This 50 horsepower motor will grind 22,000 pounds an hour of coal. The main fan for the air system is also connected to a variable frequency drive so that the distributive control computer can adjust particle size and fineness upon demand. More airflow results in a coarser product, thereby allowing fuel size flexibility on demand and minimizing carbon loss. The outlet air temperature is controlled to approximately 120 degrees Fahrenheit, while the inlet temperature is approximately 350 to 400 degrees Fahrenheit, thus drying the 27% free moisture in the coal down to 9% and transporting the finished product to this cyclone, where the solids are removed from the airstream. This system is known as semi-direct firing system, in which the fuel is pulverized in an air-swept DFM mill and then is separated from the air in this 9-foot diameter cyclone. The fuel discharges at the bottom through a 14 by 14 rotary airlock and is picked up by 2 PSIG conveying air from a primary blower and is conveyed directly to the ASEA Stahl boiler. For the purposes of this video, a product sample is obtained. As you can see, the system is under 30 inches negative pressure. Normally, a 7-inch cyclone is attached to this pickup probe, but the coarse fuel requirements would not allow the older design to work efficiently. Instead, the probe tube is capped to prevent the egress of air, and a representative sample is obtained. This Wyoming subbituminous coal, with a feed moisture of 27%, has been dried to 9% moisture and ground to 99% minus 1/4 inch, with only 2.3% minus 90 micron, and an average D50 particle size of 1,350 microns. 2 psi transport air now conveys the prepared fuel to the Aciastol distribution center inside. Here, distribution of the coal and air is made into 10 separate 3 1/2 inch diameter lines. Each of these lines then traverse under the boiler to its appointed fluid bed area and is again redistributed into 4 separate 1 1/2 inch diameter lines that feed up into the bubbling bed above. This then is the Aciastol bubbling bed boiler, rated at 150,000 pounds of steam per hour, with a steam pressure of 1,500 psig. This boiler provides steam for this plant, and by means of a separate turbine generator, manufactures 9.8 megawatts of energy for internal consumption.
Now change the graphic over to show everything in color. Essentially what the graphic shows, command of the boiler, outlet temperature of the pulverizer, you have a classifier which shows the classifier speed, differential pressure, inlet, air temperature, airflow, mill speed, mill amp, feeder command. Main panel for the fiber screw wave out feeders. Essentially what it tells us is we're running 24 to 25% demand at 275 pounds per minute. Okay, this is our distributor plate. In here you see material, which is limestone. The material falls through a feed chute down on this deflector plate onto the distributor plate. The distributor plate then slings the material off the outer edges down in. Here we have the journal assemblies, which rests on top of a spider. The grinding action takes place down here between these grinding rolls and what we refer to as a bull ring.
For the purposes of testing the Williams direct fluidizing mill concept, Compco has allowed Williams to modify this plant as will be shown. The purpose is to minimize 100 micron fines while crushing to variable product sizes varying from 1,000 microns all the way down to 300 microns average particle size. The coal is stockpiled in the open by means of a radial stacking conveyor and is recovered by a front-end loader and transported to a feed hopper equipped with a vibrating output feeder located at the bottom. The coal arrives at Compco's plant by railroad hopper car and is normally a -3-inch feed size.
Coal feeds down the hopper into the Williams 240 reversible impactor. The pulverized coal then discharges, drops onto a conveyor. This conveyor takes the pre-pulverized coal on up to the large feed storage bins for the pulverizer.
The pre-sized coal drops into one of two 100-ton storage bins. A gravimetric feeder is located directly below. At this time, the coal consist is 80% -1/2 inch, 57% -1/4, and it has 5.3% -100 mesh.
Okay, feed drops out of the large feed storage bin onto the weigh belt feeder. This feeder is running at its maximum at the present time, about 20 tons per hour. The feed is around 2" by 0. It's got from 8 to 10% moisture. The feed drops off of the belt down the chute into the mill's feed chute.
Directly below the feeder is the Williams DFM pulverizer that has been modified for this test.
Okay, feed enters the pulverizer through the chute back at the back of the chamber up above. Feed slides down the chute and drops onto this distributor plate. The feed is spun off the distributor plate, dropping over and where the fines are stripped away by the upflowing airstream. Okay, the feed drops down where it collects on the bottom of the mill and is fluidized by a combination of the plows turning with the mill's rotation and is fluidized by the air which enters tangentially through the wind ports from the wind box.
Coal containing 8% or even 14% moisture can easily be reduced to less than 1% in this system. To the right we see the input feed chute that connects to the gravimetric feeder located above. And now we have a sample of the top discharge of the DFM pulverizer. This output represents normally 1/2 of the total feedstock and has been dried down to less than 1% moisture. This product now contains all of the fines, both in the feedstock and those generated by the pulverizer. These fines have less than 1% moisture content. And
here underneath the Williams 74-inch DFM mill, the mill is powered by a 500 horsepower motor through a Falk right angle gear reducer. The mill speed is varied through an AC variable frequency drive. The chute right here is for discharging material off the bottom of the mill. The material drops down out of this discharge chute through a open or closed slide gate and drops into the discharge conveyor.
Bottom discharge, you can see right down here, it's coming out of the bottom of the mill, being transferred into the front end loader via a slider belt conveyor. You can see there are relatively few fines in the bottom discharge, less than 0.1% minus 200 mesh.
50% of the feed reports as product to the bottom of the DFM pulverizer. So now, if we mentally combine both the top and bottom discharge of the pulverizer, we have a product that is dry and that is 98% minus 1/2 inch with only 10% minus 100 mesh, of which 5% arrived in the feed material.
Okay, today we're going to demonstrate our laboratory front feed wood hog. First thing we have is a Kinergy vibratory feeder with a 12-inch wide pan, approximately 12 feet in length, powered by a 1 horsepower electric motor. The feeder introduces the feed to the Williams C17 front feed hog at this location. This feeder is specifically stiffened at the nose end here to withstand the pounding that it will receive because it will be in close proximity to the mill hangers. Installed at the front of our wood hog is a catch pan because a small amount of wood always escapes through this opening. We have to have clearance around the feeder. This catches most of the wood that escapes from the feed opening and actually sucks it into the bypass air pan. Prevents a housekeeping problem and gives you a much cleaner operation. This is the Williams C17 front feed wood hog. This is powered by 75 horsepower and operated through a V-drive at approximately 1800 RPM. Today, the machine is equipped with our standard wood hog hammers and a set of 1-inch grid sections. Material ground by the hog enters an air pan that is nested between these mounting channels. Comes along here through the adapter, through the pipe, and into a pressure blower that blows the air and the wood into a cyclone collector. Most of the wood discharges through this bag into a 55-gallon drum. The slight portion that is not trapped by the cyclone comes out the exit pipe and is trapped in this second air bag. This is the material we're going to process today. We have some heavy 2x8s. We have some thinner wood strips, approximately 1/8 inch thick. We also have an assortment of 2x4s and 1x6s. Also, we have some standard 4x4s and some 4x4 Walmanized landscaping timbers, some 3x6s or 4x6s, and an assortment of light-duty pallets that have been pre-cut for use with our narrow laboratory 12-inch wide feeder.
Turn the vibratory feeder on first. Now on. Turn the fan on next. On.
what you seeing?
Okay, this is a nice minus 3/4 to 1 inch length product that is approximately passing a 1/4 to 3/8 square hole test sieve with very few splinters.
To the left, you see the switch yard with the coal unloading facility, rail unloading for coal and limestone, coal storage facility, reclaim, conveyors up to the boiler facility. Coal being received by bottom dump rail cars. The cars are positioned by a car puller, unloaded to underground hoppers. The material then is transferred by belt conveyor up to a transfer point where the material can either go to the boiler directly or stacked out to a storage area. Material then can be reclaimed from the storage area and transferred back onto the conveyor system and transferred then onto the boiler. As you can see, some of the coal is a little bit larger size, probably 4 to 5 inch.
A conventional crusher mechanical feeder system, this mill would probably be shut down now because of the moisture content, those surface and inherent in this type of coal feed. We're told it's running 18% moisture as you see it now. This system is designed to handle about 15% moisture, which means we could use a little bit of auxiliary heat.
The coal bunker, and the coal bunker has air cannons on it, and at the base of the bunker, at the discharge, we have a vibrating bin discharge. The bin discharges to a downshoot with a shutoff gate, and then directly down to the stock feeders.
This then is the low-pressure gravimetric feeder that meters and measures the coal into the DFM mill located on the floor below. At the present time, the feed rate is 10.2 tons per hour. Fuel preparation for the new fluidized combustors has proven to be a significant problem. Moisture contents of up to 15% to 20% can and do cause binding and plugging in primary and secondary reduction in fuel feeding apparatus. Here the fuel is fed by means of a standard weigh belt or gravimetric feeder in the 2x0 format, containing normal moisture contents of up to 18 to 20%. The pulverizer reduces and dries the fuel to a product size desired. The final product size can be changed while in operation. Limestone is also fed into the center of the DFM system.
Limestone is transported by rail car to the plant, stored in that concrete silo, and is transported to silos inside the boiler house.
The limestone sorbent is recovered from overhead storage by means of a vibratory output conveyor at the bottom of the bin. This product then drops down into a variable speed screw conveyor, which takes the pre-sized dried limestone and meters it into the center of the DFM mill located on the floor directly below. Sorbent demand is a direct function of the SO2 as being measured at the outlet of the stack. Mixture then of fuel and sorbent fall directly down this central chute into the DFM mill located directly below. Multiple fuel outlets, as shown here, allow uncomplicated fuel splitting. A combination of coal and limestone therefore then land in the center of the DFM system, landing on a feed tray supported by the spider. The solids are spun off centrifugally into the upward rising airstream. Pre-sizing takes place at this point, and material that is already to size is caught up in the airstream, thereby bypassing the grinding elements. This pre-stripping of product helps minimize oversized grinding and the generation of extreme fines, and results in lower horsepower per ton. The coal is crushed entirely by rolling contact between the roll and bull ring. For a circulating fluidized bed combustor, this is the world's first direct firing fuel preparation system. The Williams ring roller mill direct firing approach gives excellent control over particle size analysis, coupled with drying, mixing, and distribution of the fuel and sorbent. The vertical shaft is driven by means of an external right-angle gearbox and drive motor through couplings. The motor is connected to a variable frequency drive so that the vertical shaft speed can be varied from 0 to 100% speed. With the bottom discharge as shown here, beneficiation can be incorporated with the removal of impurities, pyrite or tramp metal, and this is accomplished with the bottom mill discharge. Automatic lubrication is accomplished while the system is running. Multiple outlets can be supplied so that even distribution of coal can be made to the CFB. Due to the rotational speed of the DFM mill, the swirl imparted to the rising air through the wind box area and the limestone and coal particles are evenly mixed and transported to multiple outlets.
The two DFMs and is split into 4 sections, one to each of the side walls of the combustor. The coal is very, very simple. It comes up and is blown in essentially at the end of a pneumatic pressurized pipe. It's blown in on a slight negative dihedral so that it promotes mixing with the upcoming fluidizing air coming off the grid down below.
For the purposes of obtaining a representative sample, a typical cyclone coal sampler is utilized on the outlet duct. The D50 is now 934 microns. So it's basically laying right in here on this material. Nice, coarse, granular material. These are the fines, 18 mesh,
50 mesh, all the way down to the 100 mesh shown here, and this is minus 100 mesh. And there's only 11.8% minus 100 mesh with a D50 of 934. Now at maximum continuous rating. The air coming in. 964 degrees. The set point's 974. Mill delta pressure is 8.1. Design is 8.0. 91% full load amps. Bed temperature is 1611.
The sludge is pressed and majority of the water removed. The sludge then is transferred by belt conveyor up to a surge bin where the sludge is metered into a conveyor system, and the conveyors then transport the sludge to the boiler building.
This is a picture of the in-feed conveyor for the de-inking sludge from the press building. This is the largest volume of recycled sludge burned anywhere on the face of the earth. This boiler is rated at 46% MCR on just de-inking sludge. Most units hold 4, 5, 6%. This one is obviously the largest made. What we're looking at here is fluffed material that is about 55% solids. This is the bottom of the cyclone where it comes into a non-mechanical loop seal, which is essentially a U-tube manometer. From there it is additionally fluidized with 100-inch air for these lines you see here. And then it mechanically goes back up, which is part of the U-tube manometer effect. And then it slides over a hump and goes down into the bottom of the combustor for the final recycle. Otherwise, the pressure from the furnace would blow back up through here and would not have a differential pressure seal with the cyclone. What you're looking at here is the sludge feed points coming in by mechanical conveyor from the sludge press house next door. It's fed in and is evenly divided into the two loop seals. The hot return material coming back from the cyclone is coming down through this loop seal at about 1560 or 80 degrees. And at that point, the sludge is laid on top of it to promote immediate heating, drying, and mixing with the hot recycled material. This is the secondary air inlet, which is used to pick up some heat by natural convection, conduction, and radiation off of the upper portion of the bottom ash hopper, which does not have a water-cooled screw. This is the first installation in the world without one. As you can see, it's not required, and the air is picking up only a very, very small amount of heat, and is conveying that heat along with secondary air through this duct over to the inlet of the secondary air fan. This is all very conventional pneumatic ash pickup material where the hot solids out of the bottom of the combustor, the rejected solids inventory, is conveyed pneumatically out to the ash silo for disposal in conventional pneumatic fashion. A sample of the coarse material that would come from the bottom ash drain on the combustor. As you can see, it's fairly small material.
The ash is pneumatically conveyed to the top of this storage hopper, where it is removed at the bottom by a conventional dump truck to landfill.
The building on the right-hand side behind the rail cars is the turbine generator room. Coming across is the power plant offices and control room, which is just beyond the transfer tower for the sludge and the coal. Then is the circulating combustion boiler by Pyro Power, which has the elevator here on the outside, its extension. Then to the rear of the building is the entrance to the Savinska Flak-Fabriken rigid frame precipitator, followed by the ash handling system and the large circular silo on the far side, the tan silo, and then the brick chimney for the unit.
This is the steam generator building, where a 48 megawatt steam turbine and generator is utilized to provide part of the energy utilized by this plant.
The big object on the right is a HRSG heat recovery steam generator. Has its own stack, of course. It's connected to a 40 megawatt General Electric gas turbine, which on the left-hand side, the tan part on the left-hand side, are the inlet filters for the gas turbine. Has a bridge crane over the turbine. And it is connected electrically through the proper distribution grid to the steam turbine, which is the building further to the left, just behind the switch yard, the gray short building in front of the boiler. These two turbine generators provide most of the electric power necessary to run this paper mill, which makes it essentially electrically self-sufficient, or energy self-sufficient for that matter. They have to buy coal. They mix the coal in with their own de-inking sludge. The de-inking sludge has a net heat contribution to the steam generation process in the Pyro Power circulating fluidized combustion unit. Therefore, Southeast Paper is utilizing waste material, landfill material, to generate steam, to produce energy, to run this plant. The entire plant runs off of recycled waste paper, so this is really an environmentally friendly paper mill.